Hello, AP Physics C students. Okay, so this is the final video from today, March 12th. You have the notes page in front of you about Lenz's law, so I want you to read that if you haven't already. Read the wording of Lenz's law, and then we'll discuss. Okay, so that didn't make a whole lot of sense, right? Don't worry, we'll go through a bunch of examples and I'll show you how Lenz's law works. But it's really all about the negative sign. Faraday's law says that the induced EMF equals negative N d phi d. We just totally disregard the negatives, and even because everything's a scalar, the negative sign doesn't exactly have meaning. It really just means the opposite direction from something that was originally established. And yet the negative sign is there. It is part of the equation. So Lenz's law helps us understand it and takes everything from a different perspective. And this guy Lenz got an entire law named after him just for explaining a negative sign. That's pretty cool stuff. Okay, so the whole idea is about maintaining the status quo, that when you change something, the universe doesn't like that. The universe never likes change. And so while you're changing something, the universe is going to do everything in its power to put it back the way it used to be. And it's all about magnetic flux. So let's look at this picture here. What we're seeing here is a loop of wire that has no source of voltage. And this is not one of our imaginary sources of voltage that I just leave off the picture. There's no source of voltage. It's just a loop of wire. It's in a rectangular shape. We're looking at it sort of in 3 dimensions. So this is the near side. This is the far side. Hopefully you can visualize that with perspective. Here's a bar magnet, and I apologize, the N for some reason on the North Pole didn't print very well on this or on the notes page. But anyway, we're taking a bar magnet and we're going to put it through the loop. In fact, this is very much like the very first demonstration I did, where I had the bar magnet, I put it through the loop of wire, connected to the galvanometer, and it registered some current. Well, eventually it did once I put a whole lot of magnets through. So here's the idea. We're going to be going through a series of steps to look at the initial direction of the field, the change of the field, and the induced field. Because that's the whole idea, is that there's going to be some field present. We're going to change the field. The universe is going to try to create a field to oppose that change. And to start off, we look at the magnet. You can see that the north pole of the magnet is close by the area of the loop. And so first we want to do is draw the field produced by the north pole. So if you need to go back in your notes and review that, do that, and then come back. Or hopefully you just remember that near the north pole of the magnet, the field lines point out or away from, right? So here's some of the field lines near the North Pole pointing out of the North Pole, sort of in curved shapes over here. But in general, they're pointing kind of down, right? So in this region, if we were to register the magnetic field, it is pointing down. So the initial direction of the field is down. Now this arrow says we're taking this magnet and we're moving it towards the loop. So then we want to see what's the change in field, which then causes a change in flux. Well, if the magnet is originally far away, we're bringing it closer and closer to the loop. Does the field near the loop get stronger or weaker? Well, of course it gets stronger. The magnet is getting closer and closer, right? And so the change in field is down as well. If that bothers you, think about it in terms of velocity, right? If an object is, let's say, moving down and accelerating down, that's getting faster and faster down. It's getting more and more velocity in the down direction. So here we have a field that's already down. We're moving it closer to the wire, so the change in field is also down. It's adding more field, a larger flux because of the more field lines inside the loop. Okay, now the universe says, well, if you're adding extra field lines down or putting more flux down, then it's going to try to oppose that by inducing a field that points the other way. Here's Lenz's law right here. Here's the negative sign, that the direction of the induced magnetic field opposes whatever you're doing to change the flux. Now, how does it do this? Well, we know all magnetic fields come from currents, so it's going to create a current. The universe will create a current inside the loop, one way or the other, to create a field that points this way, to oppose the change. So now, here's where we get into the right-hand rule shortcut, or if you want to try to grab the loop in different locations so that you can figure out which way the charges are flowing in one way or the other to make a field that points this way. Try it on your own. Alright, so hopefully you figured out that the field lines, the current is pointing this way. Sort of, if we're looking at the loop from above, it's going in a counterclockwise direction. So if you follow charges around this way, so that in the nearer part of the wire is pointing to the right, with your fingers, your thumb's going to point up, creating a magnetic field to oppose the change in flux. There's Lenz's law. That's how it works. Let's try another example. Let's say that this magnet continues to go through the loop, and now here it is with its south pole near the loop, and it's moving away from the loop. We're going to go through the same steps. The initial direction of the field, the change in the field, the induced field, and finally the current that creates that induced field. Let's start by drawing field lines near the south pole. So pause the video, draw them for yourself. So you should remember, of course, that field lines point inwards towards a south pole, down and in, sort of like that, which means the initial direction of the field near the plane of the loop is down. Right? Most of these field lines are pointing down. Now, we're taking this magnet and we're moving it out of the loop. We are moving it away from the loop. So what's the direction of the change in field? Hopefully you said up. Right? We're taking these field lines and we're removing them. So here's an example. For example, let's say it's moving down but slowing down. Then its change of velocity is the other way, right? So if the initial field is down and we're removing those field lines, then the change is up to get rid of them. The universe says, wait a second, there used to be a field pointing down, you're taking it away? Let's put it back by inducing a field that points down. So again, the induced field always opposes the change in flux. So now I want you to figure out what direction should charge move around this wire to create a magnetic field that will point down. So again, by using the right-hand rule or by grabbing different points of the wire, we should have gotten that seen from above. Now charge is going to flow around in a clockwise direction. So that in this nearer part, the charge is moving this way. Follow around here with your fingers. Your thumb's going to point down, creating an induced magnetic field that opposes the change. And that's really what Lenz's law says. That negative sign says that charge is going to move around to create a magnetic field that opposes the change. Whatever you do, the universe doesn't like that. So here's another example. This should look awfully familiar. So I want you to draw this one more time in your notes. We are once again looking at our movable conductor of length L sitting on top of these conducting rails. We'll assume they're frictionless. Remember, we're looking down at the situation. We're going to move it to the right, and here's that bar sometime later. And now we're going to look at this from the perspective of Lenz's law. We're going to go through the same steps. Initial field, change in field, induced field, and current. You don't always have to do this for Lenz's law. I just find it's the easiest way to think about it. Yes, of course, flux doesn't always change by changing field, but watch how it works in this situation. Okay, what's the initial direction of the field? Well, here's our original loop this way, and obviously the field lines are pointing into the page, so there's X. Now look, we move this bar over. What is the change in field? Pause the video and write down what you think it is. Did you say into? It should be. You can literally just count up the x's. 1, 2, 3, 4, 5, 6 x's originally, and we add 3 more, 1, 2, 3, 4, 5, 6, 7, 8, 9 x's by moving the bar over. We've literally put more x's in the loop, in the area of the loop. But when we put more x's in, the universe says we got to take them away by inducing a field pointing out. You put x's in, the universe tries to take them away by creating a field pointing out. So now I want you to do the right-hand rule, shortcut, figure out what direction the charge is going to move to create this field. Pause the video, try it on your own. Okay, and hopefully you got counterclockwise. You follow charges around a counterclockwise way with your right-hand fingers. Your thumb will point out of the page. That's the induced field, which means charges are flowing around this way. Now, go back to any of the other pictures that look just like this, whether they're in your notes or in your problem set, and you should see that matches. Which means, if you don't get any of this Lenz's law stuff, when you want to go back to the original way of looking at it, that's fine too. Remember, the original way was looking at an individual proton inside this conductor. The proton's moving to the right, inside a magnetic field into the page. It feels a magnetic force to the top of the page. Protons collect over here, and when they connect to the wire, charges flow out in this direction, going around the circuit in a counterclockwise direction. So you can get the exact same answer from the perspective of looking at the magnetic force on the moving charges, or by doing this whole Lenz's law thing. You can get the exact same results. So some students like it one way, other students like it the other way. It's up to you, however you choose to do it.